open questions on the software, hardware, anything you have questions, you please free. And we have 3D experts here and pseudo 3D and in situ. So anything can be asked. Okay. Yeah, don't ask for, I want to measure or I want. Yeah, now it is time for interaction or any clarifications or any. If you need to know about systems and prices, we have here Arjun. Yeah.
I have a problem in the OEM software, like when we are performing TKD, some of the press plates are diffracting and we are getting the raw patterns. But when we are indexing in the OEM software, it's not even indexing, it's completely becoming black. When we are performing TKD, like whatever some of the press plates are getting diffracted, but it's not even indexing. But in the team software, when its scan is going on, it is indexing. But when in the OEM software, it's not even indexing. Means in the analysis part, like whatever the press plates, it's not indexing as any BCC phase, any press plate like that. But we are getting the patterns. Are you saying the patterns? Yeah. And what does the pattern look like when you look at it for that point? BCC phase. But there is a pattern there. Yeah. And it's recognized. But the pattern does not belong to the phase that. No, it's. But means this is happening when we are performing the TKD on the APT tip, but when we are doing on the TKD on the lamella, it's indexing. Yeah, I think I'd have to see the data to try to understand that.
A PowerPoint and some data and send it to Arjun. If he can't figure it out, he'll send it to me and then I'll take a look at it. It sounds like it's, I don't know if it's a procedural problem or a bug somewhere. We'd have to check. If you do have problems, please talk to Lakendra, talk to Arjun. They'll pass it on to me if they're stumped, and then we'll try to solve the problem. But I can't solve them all by myself.
I have a question related to the pseudo symmetry which was talked about earlier, like yesterday's talk. So I have a Lave's phase C15 CR to NB Lave's phase in my material, so along with multiple phases. Okay. So when I tried to index the Lave's phase with the existing standard files that was available, I was not able to get it indexed. Okay. So I tried to generate a pattern and then I tried to do it, but it was just coming as dots. It was not indexing properly. So do you think this Lave's phase is it is not indexing because of the pseudo symmetry, or could there be any other?
But the patterns look okay?
I think so. It was. Okay. It's a deformed sample. It's really okay. Faint.
It's pattern. Really faint, but yeah. So if you can see the bands in the pattern, my guess is the structure file that you're using for the phase has probably not been optimized correctly and doesn't have the right reflectors in it. So that's challenging to do because you kind of need a good pattern to check it on. But that's usually the problem when you have a material like that that's probably not well understood in terms of EBSD. Has anybody else worked on that with EBSD? Okay, so you might be the first one who's done EBSD on it, and that's figuring out the structure files is a really challenging thing.
Yeah, maybe not in a multi-phase material, maybe separately they would have dealt with it.
Can I interrupt? Yeah, we did some on the Lave's phase, but how did you enter your structure data? Is the wake-up potentials of interest?
No, I have have done XRD. So from the standard file, I know what is the vector.
So you generated the zip file
Huh.
and fed into the EBSD.
Yes.
I would suggest that you find out the weak off positions and feed into the EBSD.
Oh, you mean I should do rich build analysis to get that?
Yes, do the rate welt analysis, get the weak off positions, and then put in the EBSD. You will be more accurate.
Okay.
This is what is our experience.
But yeah, with one more
Maybe.
problem is it's a multi-phase material, so I tried doing rich build, it was not coming properly.
Oh, I see.
Yeah.
Do you have the atom positions?
Okay, high entropy. Okay,
Yeah,
it's a high entropy.
It's a high entropy material, yeah.
That is something.
Yeah.
The background correction in EBSD is a very, very gray area.
Yeah, it is
It
great.
depends on the user.
Hello. Sometimes you don't get a background properly.
Right, yeah, with TKD, it's really hard to get a good background, you're right.
Try to get background to contaminate sample.
Yeah,
Also, it depends on the thickness of the specimen.
yep, it's changing across the sample.
Yeah. Sir, we are talking about 3D BSD. As we don't have that facility with us, and let's suppose sample will preparation. So if I clean some area of the sample in FIB and I take it out to the BSD, so is that going to work? Let's say I have two different facilities. So if I clean some area in FIB and I take the sample to do EBSD in separate machine, so is that trick is going to work?
No, you are doing FIB, then
Like
you are doing FIB in a machine and
Yeah.
doing EBSD in a different
machine. So let's say I select some
Is that the
area in
question?
FIB and I drill some to 20 nanometer. So I clean some area and some particular depth, let's say 20 to 30 nanometer, because that's what I think the pulsing strain will be removed. Then if I do based on the same area, so will it work or not?
So his question is, what his question is, he's doing a FIB, and the FIB is done in a one machine, and then on the same area he wants to do an EBSD. Can he do an EBSD on the same?
I mean, when you have taken out a FIB sample, right, what would be the kind of dimension? Something like 10 micrometer by 4 and 5 micrometer, yeah? One rectangle. So there is no region of interest going out, right? There is a very small area to do BSD, so you do not have to. Once you have done a FIB, you have already chosen a ROI, right?
No.
I'm not getting the question. I'm actually not getting the question. If you can.
I don't want to drill a lamella. Let's say I will select some 10 micron area.
Okay.
And I will drill some to 20 nanometer depth, so that.
No,
that
one
area-
minute. So you have taken out a 10 micrometer lamellae.
Not-
Did you pick it up?
No, not lamella. If only I will clean the surface.
Okay, clean.
I will clean a area
Yes,
of
clean.
10 micron,
Hmm.
and the cleaning depth will be 20 nanometer, 30 nanometer.
Okay, you have gone to depth and then cleaned. Yes.
Yeah. So is that cleaned area will be out of strain, and so should I get perfect patterns?
Yeah, I am getting your question. You are getting your question. So basically, once you have fibbed your sample, whether the surface is good enough for EBSD, yeah? So that is basically your question.
Yeah, that's not in the same machine.
No, it is not machine dependent, it is a surface, quality of the surface. See, if you have fibbed down to 20 micrometer, obviously you would have used current something like, I don't know, maybe 35 picoamperes or 20 picoamperes, otherwise it will take a hell lot of a time to go down to that depth. So once you have done that, so your depth to which damage is created is of, no, he said micrometers.
Area is in micron and
Depth
depth will be
is?
nanometers. So to 20 to 30
Depth is
nanometer.
nanometer. If you are using a small current, say I'll tell you the depth of damage is almost similar to the current that you use. If you use 7 picometers, it's 7 picometers down,
Yes.
the damage. That's roughly
Yes.
rule of thumb. So you use 7 picoamperes, and then your surface will be very good.
Very good.
You use something like, let us say, start with something like 15 kV, 7 picoamperes, then go down to 5 kV and stick to the 7 picoamperes.
Yes.
And do these steps step by step, your surface will be very good for EBSD.
It's basically the same idea
Yeah.
as polishing.
Yeah, you are polishing. And the angle that you are doing matters, okay?
Yeah.
So if you are doing it end on, and you are cleaning the surface here,
Yes.
it's not going to work. Your surface will be very bad, because you are continuously redepositing. So you are always advised the way I said, so you have to clean it like this. Yeah? It should also always look at a grazing incidence.
So the
Never do this way.
angle of the beams so
Grazing,
should not
you have
be
to have it grazing.
perpendicular. Grazing angle. Okay.
Yeah, you have your sample, you understand?
Yeah.
So it has to graze.
Like this.
Yeah, something like this, yeah. So that's why I said, if you take a Cadbury wafer, yeah, you eat it like this, yeah? So it is this edge that you are going to polish, not this edge. Always do this edge.
The other issue you might have as you move it to a different machine would be the oxidation, depending on the material. So you might lose all that nice work you did fibbing, polishing, if it oxidizes quickly.
Well, you have so many dwell beams, why do you want to go to another machine?
So can we measure the amount of residual strain present in the material using EBSD?
You can measure the indication of strain and the relative amount of strain from grain to grain or point to point within the microstructure, but you cannot measure the absolute amount of strain. You can't give it a number that says it's strained 3%. That you cannot do. But you can say this grain strained more than the grain next door.
The CAM value.
CAM value, yeah, it's probably the best thing to use. If you're just interested in the grain, from grain to grain, then you might want to use GOS. And that's kind of nice because there's more statistics involved, where CAM is just really, 1 point at a time. So the precision of the measurements is less affected in GOS than in CAM. CAM's more sensitive to the precision of your orientation measurements.
Yes, he asked residual.
Residual strain, I thought he said.
That's another story. He's not just looking at strain, he wants residuals.
Sir, my question is related to the yesterday's class discussion. Actually, the TKD can be done with the help of the EBSD and TM also, you said yesterday. But why using the TKD, apart from the Kikuchi band, we were getting other minute details also. Okay, so why in Kikuchi band we are getting with the help of the EBSD. So only the dark and bright band we were getting. So actually that was because of the elastic and inelastic scattering of the electrons. So that main Kikuchi band. But what about that other bands we were getting? So is that we were getting that another band is due to the elastic and inelastic scattering of the electron, or another electron was also participating at there? That is my question. Please.
You guys have asked tough questions. So Mark DeGraff has started trying to model TKD, and it's not as easy as he thought it was going to be because of these types of issues. Did you see any spots? Sometimes if you have it thin enough, you might start to see the spot patterns. And so then you have also the interactions that are creating spots and the Kikuchi bands. I don't really know yet, and I don't know where to point you to, because your question is very new in terms of what's been done in the modeling side. But I would watch and see, look for papers by Mark and Imo Winkelmann on the process, because they're both trying to work out the TKD model, and they're not really sure. It's it's not pure Kikuchi diffraction like in the TEM. It's something a little different, probably because you're going through a thickness and you're getting some scatter that you don't quite understand yet. And so I'm sorry, but I don't have a great answer of if it's elastic, inelastic interactions or not.
Maybe I have a comment. I think you just have to keep it as inelastic as possible. It's Kikuchi after all.
Yeah.
So make very, very thin samples. It has to be a little bit thick, because if you make thin samples, as Stuart says, you'll start saying diffraction spots. And diffraction spots in a TEM, you are almost doing a TEM-like thing, yeah? It's already dynamical effects. So I would suggest that go farther. It should be a little thick so that you get a lot of inelastic scattering is what you are looking for.
Yes.
Not elastic scattering.
Okay, sir. And another question is that in TM that we are defining that this Kikuchi band is between between the plus minus G. So is this kind of possibility is there at that EVSD also, like, is that?
Bandwidth.
Yeah.
I don't know.
I think if you're, to get that A plus C problem, I think you're probably going to have to go to the cross correlation type stuff to really answer that. I just don't think with, Huff-based indexing, we give you enough precision to address that problem. And your point's a good one. Either go thick and do Kikuchi, or go thin and do spot patterns, but don't go in between. You can't have both. The software packages that are out there just can't handle it.
But this plus minus G thing, we use it in ECCI, isn't it?
Yeah.
The contrast
Yeah, you do.
because of this only.
Yeah, and that's another, that's another way to answer the question. If you don't want to use these diffraction methods, I guess it is a diffraction method, but is ECCI, if you're familiar with that. If not, let us know and we'll point you towards it. In that, you're taking your sample and you take a G vector that tells you how you need to tilt your sample and to satisfy G dot B, and then you can look for dislocations that way. It's a little more cumbersome and more work, but it does give you an answer that you probably can't get. Yeah, good point.
Any more questions? Yeah.
So this is not related to texture. It's about the shear banding that you were talking about in the tungsten heavy alloy. So was it observed in compression or tension or?
No, this was in rolling.
Or rolling?
Rolling. So in rolling, you always get shear bands. Okay,
Yeah.
so there are like copper type bands, micro bands. So banding also occurs at different length scales. And at IIT Madras, probably the expert of banding is Professor Shivshambhu Mahesh. He has a very nice tree type model that he has built up. What we are trying to do is to look at the stress distribution, and shear banding really takes up. It's like when you talk about we say that slip accommodates plastic deformation, but it's not just slip. Slip is also a subset of all shear based processes. Like slip is one part, twinning is another. You get micro banding within the grains, you get deformation bands, you get shear bands. So what we are trying to do is that in the microstructure, if we see a shear band which is forming, with our simulations now we can look at what is the stress distribution. What I showed you was a 1 mysis stress and 1 mysis strain, but I can go back and look at say sigma 11 or sigma 22. These were from 2D, but nothing stops me from doing it in 3D. And then I can say that, okay, this part of the microstructure, this stress is high, and therefore the shear band is nucleating over there.
No, actually I am working on this refractory high entropy alloy. So in the sample I have done uniaxial compression, so using labels. So I do see deformation bands across the sample.
Okay.
So I just thought it was observed in tension or compression.
Okay, but are you able to make big enough samples for tension?
No.
No, that's the problem.
It's,
yeah.
powder metallurgy.
Powder metallurgy, right? From SPS, is it?
Yes.
But there are miniature tensile testing, because people do HPT, and we can cut, which is probably even smaller than what SPS diameter is, what, like 8 mm?
No, maximum dia I have is like 25 mm diameter.
That's quite large. You can easily cut a micro tensile specimen and do a tensile test with it. It is possible.
Thank you.
Sir, it's a general question on the strain measurement. So if I have a sample which is coarse enough, so it's having coarser grains, and which I am measuring which I am using for EBSD analysis with a larger step size, and if I have the same sample which is severely deformed, having a recrystallized finer grains, which I am analyzing using a smaller step size, when I am doing the strain analysis, what kind of precaution should I take so that these measurements are comparable?
So in your CAM measurements, I would adjust them so that would approximate the same distance. So let's say in one sample you had a step size of 1 micron, and in another sample you did a step size of 2 microns. And the 2 micron step sample, I would do first nearest neighbors in the CAM, and in the 1 micron step size, I would do second nearest neighbors in the scan.
Apart from CAM, there is everything else can be done without changing any parameters.
Right, yeah, I think so. And the question we had earlier over here about residual strain, just a comment to that, there has been some work out of Japan, I believe, where the idea is you measure the CAM in in a big area over a lot of grains. And then you take your strain, your bulk strain for the sample, and then you scale every grain based on GOS or based on CAM, whatever, and just kind of interpolate, say, okay, it has this much GOS, so that's, if that's a fraction of whatever for the total, fraction of the sum, then you can apply that and say that's how much strain's in the material. But that's a pretty crude approach, I think. I'm not sure it certainly doesn't take into the account that within the grains there's differences in strain as well. Not just, that kind of assumes that every grain's the same, acts the same throughout the grain, so it's homogeneous within the grain, which I don't think is necessarily a great assumption. So it's one idea that's out there, but I don't think it's well proven yet.
Thank you, sir.
Any other questions? So we have a small presentation of questions. So we projected some pictures are there.
We found that there is not orientation specific also.
Okay.
We tried adjusting, playing around with the bin pattern size and the theta, but still we are not sure what is the optimum value that we should use to eliminate these stray artifacts.
So in that case, it looks like the IQ is a little lower too, did you check and see?
In other cases, the IQ is perfect, but we still find these.
So it's not a pattern quality effect that's going on. When I've run into these problems, it often has to do with our pattern shift. The calibration, the pattern center, is shifting as it moves around the sample. So I will try. We'll see how my artistic skills are today. So there's something called the pattern center. And the idea here is that the beam hits the sample here, and it comes over here to the detector, and this, you take the normal to the detector to there, and that becomes what we call the pattern center. So in 2D then, the pattern center would be right there. And so we call this point X star, Y star, Z star. Z star is this distance. This is Y star, which is right here, and X star. And so then you can imagine we deflect the beam, right, to do a scan slightly. And so what happens is now it's changed in Y star. And what I've seen when I've looked into these problems closely, and I'm actually working on this right now, trying to improve this, is when I see something like this, it sometimes means that something's gone wrong. So we have an algorithm that figures out what this change is. And we seem to have a problem that in some areas it seems to be going wrong. It can also mean that our original one we base it off of is slightly off. And so I think this is usually due to that effect. Why it's localized is the part I don't understand. But if I what I find is if I recalibrate it and maybe even redo this pattern shift calculation or PC shift calculation, that it tends to fix these problems.
In certain cases, we also find a high angle grain boundary, like greater than 15 degrees.
Yeah, I don't know what would cause that. That has to be a misindexing of some kind.
But that's also localized, found in few grains and not.
That's strange. Yeah, I don't know why that would be. What I would recommend is save the patterns for something like this, and then we can have a chance at trying to figure out what the problem might be. You know, I don't know if it's, I assume you're doing standard background correction, just a static one. You don't have any, do you have any scratches on your phosphor screen? Okay. That shouldn't cause localized problems, but it could, because in some grains, that scratch could lead to a misidentified band.
Can you just go back to the, this is not a normal alloy, it is Cantor alloy, it contains 5 elements in equal proportion.
But this problem we see in nickel, pure nickel. Also.
Yeah, I've seen it myself in just pure, simple.
If you do EDS, Cantor alloy.
Like this is single phase.
No, single phase
yeah.
is fine, but you would see interesting things
Yeah, I'm working on this problem. It's very strange because I'll take a data set like this.
So if you run the
and
same
reindex
scan
it.
again, that thing will appear in a different position. Yes.
Yeah. Yeah, I'll retune it and then it will work. And I don't understand why. I think I have a rounding error is my guess, but I don't know what it is. Yeah. Yeah, that's an idea. Is try a different working distance possibly too.
Okay, and the problem of grain boundary is not getting indexed. So this is a steel sample that.
So, I mean, this one is just, there's lots of noise everywhere. Oh, this is before cleanup and after cleanup. Okay. So whenever I see speckling like that, especially if it's a grain boundaries, I don't get too upset. I don't like this. That really makes me concerned that maybe I have a second phase. Maybe I just have, you know, a precipitator, some dust on my sample or something. But when I see it at a grain boundary like this, I don't get too upset because what's happening is the indexing is having a problem with two mixed patterns. For some reason, it's getting an intermediate. Instead of picking 1 and 2, it's picking some intermediate orientation. And so cleaning up that doesn't scare me a whole lot, but cleaning up this, yeah, that's scary. And I don't know what that is. So I think you've done a good job here because you've retained this problem here. Are these have low CIs, I assume? Yeah. Yeah, okay. So, yeah, I don't think you're quite right in calling this unindexed grain boundaries. I think this is a bigger region than that. I think there's a precipitate or some other phase. Whenever you run into problems like this, save the patterns. You know, it's much easier now than it used to be, and that gives you the chance to go back in and try to understand why it's doing it. And maybe there's some surface roughness right there.
But run out of hard disk space.
Yeah, hard disk space is.
It should be a few GB each time.
You should. You should buy big hard drives. Oh, okay. So maybe, yeah, it's having a hard time differentiating the two phases. Usually we don't have too much problem with austenite. Well, okay, so one might be martensite. Did you use martensite? Did you use martensite as a phase? You just did ferrite and austenite. Okay, good.
And some features that we would like to see in team.
Okay. So I didn't show you, but our next software is the software that should be out by the end of the year. We're calling Apex. And this is already in Apex. We're testing right now. We're in the final testing, bug fixing phases. So that's done right there. I think we've added manual gain adjustment back into Apex as well.
So this is something we have been trying to optimize. The higher speeds for at least annealed nickel samples.
Yeah,
we're not able to go beyond 700 frames.
Really? Usually nickel's the easiest one you're going to do. You're just not getting good enough patterns?
Yes.
More current?
With the appearance higher beam current we're getting, in spec apps you still have the beam current issue because the maximum aperture size which you have is 50 micron scale. Based on the beam current, to go high speed you need to have more beam current basically.
So new microscope with new system.
So the new MPO if you have there you can achieve 2500 up 3000 higher beam current basically.
What kind of beam current you are suggesting? What kind of beam current you are suggesting?
Around 30 nanometers.
Yeah, to go to those really high speeds, you got to pump a lot of current in. Yeah, the good news is most of those are already done. It's just we're just in the release stage and writing the new documentation. I don't know. Yeah, Arjun, do you know if people will get automatic upgrades from Team? I think if you have a new camera, you automatically upgrade from Team to Apex. No, okay. Yeah, I'm not sure.
That's the commercial time.
Yeah.
We'll discuss
Okay, I'll go back here.
You call Arjun and then lock him up in the room.
Yeah.
So Apex will be available for Apple because that's a new thing. On the velocity is available. So whoever has the velocity, there is going to be an Apex. So 2 velocities, 2 Apex.
Okay, yeah. That's what I thought. If you had a velocity, it was an automatic upgrade. Our guys in the lab love Apex. They think it's a lot better than Team. So you've seen Apex, haven't you? Yeah. What did you think? Did you like it?
It's quite good actually.
Okay.
All the features and the time of like it's much more speedier compared to the team actually. The
Yeah.
response time
And the time it takes to get a scan set is a lot faster. Right, and everybody is going to see. Yeah, we heard that. We tried to fix that. Yeah.
Any other questions? Yeah, let's go to the short.
But both has a same crystal structure, like a hexagon.
Yep.
How I would differentiate both? Like one has a HFB2 and ZRB2. Both has a hexagon crystal structure. How I will differentiate both?
How different are the C over A ratios?
Because
How different are the C over A ratios?
it's similar.
They're similar.
Because when I index that, so I choose both.
Right.
But it was indexed by one.
Yeah, and so you're getting a composite index of 0 because they're both getting the same number of votes. That's what we call a pseudo-symmetry problem. It's kind of a pseudo-symmetry in the phase problem. Can you differentiate them chemically?
Okay.
So use what we call chi-scan. Chi-scan. That's the solution.
Thank you.
Hafnium boride and zirconium boride. Yeah, I mean hafnium is always a sister of they come together.
Right from the
Right from extractions.
It's not kind of so for the last 2 days, Stuart has been harassed. So we need to say sorry. This is more revision.
Thank you. I appreciate it.
Sir, please go, please go.
I request Mukendra to come. engineering, solving our problems. Thank you all for coming, and I hope you have a very good time. It's great. Yeah, thank you. A lot of good questions. Of course, EBSD is very, very powerful, and all of you should use it. You don't have to buy it. Arjun will be happy. I'll be happy too. Yeah. So, but you're free, but he's not. Yeah. So, I think we come to the end of the session, and thank you. All of you have come from far field, wish you a safe trip back. Those who have come from hostels, also wish you a safe trip back. Thank you. Thank you, sir. Yeah. Thanks for organizing. Yeah. I think we deserve hands. Backstage support.